So raise your hand if you're actively working in the robotics and autonomy space. All right, so I see a couple of hands now. Keep those hands up. Raise your hand if you routinely use data as a part of your work or your workflow. All right, great, more hands. So you'll probably relate to this, the fact that you have lots of data and little data at the same time. Meaning it's data that's uncollected, not managed, or managed poorly, not curated, or not accessible to the right team members to be able to do their work or take advantage of that data. And I'm sure if you're like me, you may have some other adjectives associated with that problem. Without the data being in a condition ready for being AI ready, you can't take advantage of some of the technological advances. The ability to update your next generation or next version of your autonomous system is degraded. Or you may not be able to validate the systems are performing properly and predict when maintenance should occur on those vehicles. Hi, I'm Jeff Anderson. I'm the head of autonomy at AWS Global Defense. It's great to be here at reInvent 25. This is my second reInvent, my first time speaking at this event. And I'm here with a good friend and colleague, a distinguished member of the Navy. And we're going to venture into autonomy and how AWS supports and how the US Navy is leveraging AWS to tackle some hard problems. We'll end the discussion with a Q&A session. So as we go through the session, you'll see in the lower right-hand corner a QR code. You can scan that code. You can submit a question. We'll gather those questions, and time permitting, we will answer those at the end. So I'm going to start off talking about how AWS supports autonomy and defense. I'll then pass it over to my colleague, and he'll tell us a challenges and solution journey and the benefits they're receiving through operating in the cloud. Okay. So the motivations for wanting to leverage autonomous systems are many. You can look around or hear discussions about how autonomy is the future. Here in Las Vegas, you may have had the opportunity to see a Zoox robo-taxi promising to make a safer, cleaner, and more enjoyable transportation experience. That experience includes you going from point A to point B, no driver, no steering wheel, just the future of transportation. I know personally I've downloaded the app and I'm looking forward to getting a first-time experience myself. Now, additionally, some of the reasons or motivations for getting into autonomous systems could hit home a little closer. So if you imagine it's August in the Midwest in the US, families gathering for fun near a cornfield. In August, corn can be 6 or 7 feet tall. And you have a young child who has autism and a hearing disability. That child ventures off into the cornfield, and now panic sets in. Minutes turn to hours, search and rescue team called out. This is hundreds of acres of cornfield trying to locate your loved one. The local sheriff's office brings out their drone, which has a live video feed and IR sensor, and it's now 12 hours into the search. So you can just imagine what the family's going through. Eventually, the operator gets on the live feed, IR, heat signature, which then they're able to vector in rescuers to reunite the family, a true positive ending, all supported by a small UAV, an operator, and success. Now, a recent study by Accenture indicates that the drone market in 10 years from now will be greater than $550 billion internationally. In the next year alone, the US will invest tens of billions of dollars in the defense industry. Observations of what is shaping the conflicts in the Ukraine, Red Sea, and Mediterranean Sea has only heightened the sense of urgency of why getting into autonomous systems is important. They provide a force multiplication of what some have termed a hybrid force. They can operate where humans would be at risk, either due to contested areas or environmental conditions. And they enable a speed of decision which we have not seen before, gathering information and data streams throughout. And additionally, the commercial industry is heavily moving into autonomous systems. So this dual-use technology can be taken advantage of in the defense industry, leveraging the efficiency that commercial developers and manufacturers bring. They can also bring that fast-paced technology advances that we're seeing. And obviously, with investment momentum, it also helps expand that dual-use technology. Let me go back one, not done. All right, here we are. Additionally, we see some key enablers which allow the proliferation of autonomous systems. Think the cost of sensors being driven down, enabling perception at a much wider rate. The ubiquitous communications or connectivity, whether it be 5G, cellular, fiber, or satellite like Amazon Leo. Cloud computing and edge devices, which are able to ingest and process lots of data for that decision making. And then battery technology advancing, making it more scalable, affordable, and enabling longer operations. All of this creating an opportunity and the motivation for autonomous systems. But with the opportunity comes some great challenges. The challenges of making sure the systems are safe, effective, and scalable. And then how do you design these systems to ensure people trust them, that their operations are repeatable and predictable, ensuring safety when operating in human workflows. How do you scale operations to support hundreds or thousands or even more devices, generating and collecting data and acting on environmental feedback, and requiring that same TLC that machines will still require. Just because it's an autonomous system does not mean they will be maintenance free. And you can take the complexity of the robotics and autonomous system pipelines that can require continuous updates and data sets to retrain. Think autonomous navigation and how to safely navigate from point A to point B, constantly monitoring the performance, ensuring you're getting the predicted response from the system. Also, ingesting multimodal data sets, whether it be from the sensor, the vehicle, the logs, integrating disparate data sources, all being managed and cataloged in a way that you could take advantage of it. So AWS's customer obsession to work backwards from these pain points has led to services to address these challenges. So at AWS, we build the building blocks to enable customers to develop capability. Some of those building blocks could include AWS Glue, which assists in data cataloging, AWS Data Sync, which brings data backhaul at your fingertips as you deploy these devices around the world. S3 intelligent tiering. When you're bringing terabytes of data back, you do have to be mindful of the costs. S3 intelligent tiering allows you to reduce the cost of storage based on your access patterns. And then streaming services like Kinesis and AWS Elemental, which allows broadcast quality video to be streamed back for analysis. Combining that with AWS Bedrock and generative AI tools to allow that processing, analytics, and reporting. And more importantly, AWS has helped customers scale these systems globally, leveraging our global backbone for both backhaul and compute and storage. And so at AWS, engineers, they like to think in mental models and frameworks. Our framework is this life cycle of autonomy. Then going through 6 different phases, you could see how the life cycle through the digital engineering lens should be continuous, support initial designs, upgrades, maintenance, sustainment, and follow-on generation development. You should be very proud of taking a prototype autonomous system and turning that into a production system. But the journey shouldn't stop there. You're going to have to update the software, maybe update hardware components, generation 2, 3, et cetera. Operating through this digital lens will help speed to market those processes and also enable you to take advantage of the advances in AI and generative AI. So you can imagine, in their research and development phase, the need to access high performance compute, to run modeling and simulation workloads, to identify those critical features, material properties, environmental variations expected to see, the system will expect to see during its lifespan, and enabling seamless collaboration across those engineering and design teams. And then that quickly transitioning to the test and evaluation before you go to that first production phase, taking your prototype in the field, harvesting that field test data, comparing it to your simulation environment, making sure your simulation environment accurately reflects what you're seeing in the field. So improve your simulation, improve your design and capability, and then get to production faster. And in the production phase, having the secure CI/CD pipelines to enable production and integration to occur seamlessly and take advantage of things like generative AI to do cybersecurity scans, et cetera. And then once you get into deployment operations, this is where we see customers asking for help. As they scale from prototype to production, that's where you start to see a lot of these problems associated with, we tested it in this environment and not that environment. And so environmental conditions could be different operators, it could be different weather conditions, road conditions, et cetera. So having a smooth ability to backhaul that data, catalog it, curate it, and then do the analytics is essential to go from prototype to scale to production, including a global footprint. And then that same deployment data that's coming back to support current operation decisions should be harvested and managed to enable the design engineers to work on the next generation or fix engineering problems that they may see in the field. Additionally, as I mentioned earlier, machines will still require TLC. Autonomy will not remove that aspect. When do you do that maintenance? How do you develop your predictive analytics so that you're doing the maintenance at the right time to maximize operations and minimize cost and the impact to your system? And then finally, in the sustainment and logistics, managing a secure logistics pipeline and also being able to identify those critical components that have maybe not lived up to the expected life cycle and need replacement. This data can help with that logistics process as well. So when we look at the design and development, AWS provides that secure, compliant environment to accelerate design and development in autonomous systems. Leveraging the cloud, organizations can build high-performance digital twins and simulations to help in both autonomous operations planning and development. And so this slide is a little dense, so I apologize for all the words, but this is that life cycle of autonomy in in a nice kind of slide in how AWS provides services to address each one of these needs. So in the pre-deployment phase, you can consider using SageMaker for machine learning model development. You can use a service called Device Farm if you're fielding multiple autonomous systems, maybe in a family of systems, or even if it's the same system, but you have different generations of hardware in the field. You can use Device Farm to do testing as you update the software to make sure that software will work universally across that family. In the deployment phase, you can use things like IoT Greengrass, which is a runtime that can be deployed on device. You can use AWS Data Sync to backhaul that data, and there's a myriad of other services that will support this lifecycle of autonomy. And before I hand it off to my co-presenter, I just wanted to highlight, Matt Garman recently made an announcement of a $50 billion investment in AI and infrastructure support supercomputing for the U.S. government. This will add 1.3 gigawatts of compute power and capacity across all security levels. And at AWS, we build security from the ground up, and that includes for federal workloads. Now, if the list of challenges to scale autonomous systems that we've covered today isn't daunting enough, our next guest can share some challenges that many of us don't have to face. Operating in remote conditions, under the water, no communications for hours or days at a time, and the pressure quite literally of being hundreds of feet under the ocean. It's my distinct pleasure to introduce a pioneer in AI, data, and autonomy for the U.S. Navy. Dr. Jamie McGee has dedicated his life to the undersea field, first as a submarine force officer, and then transitioning to an engineer researching acoustics and signal processing. Dr. McGee is the Special Assistant for AI to the Commander of Submarine Forces, where he's leveraging AWS Cloud to develop cutting-edge technology for the Navy's undersea enterprise, including unmanned underwater vehicles. It's my pleasure to introduce my friend, Dr. Jamie McGee.
Oh, all right. Jeff, thanks very much for that introduction. It's great to be here at my first reInvent and to share some of my experiences with all of you. Really looking forward to some interaction with you at the end of this. But before I start with this beautiful calm picture of water, I want to just talk to you about two things that really keep me up at night. And those two things are pace and scale. And in particular, it's the pace and scale of AI development in the commercial industry, and as somebody in the government, how do I keep up with the pace of delivery that commercial industry is doing with model drops occurring monthly, sometimes it feels like weekly to me, and then the scale of it, which is just vast and global in nature. So critical for my team to be able to move at the speed of industry, and that's a challenge in the government. Another aspect of scale, and its physical scale that I want to talk to, resides below this calm picture of the water that you see before you. And that has to do with our undersea networks. And there's really two undersea networks that I'm going to talk about in particular. That's our fiber optic telecom networks, and then our energy infrastructure that lies beneath this surface here. So if we start with the telecom infrastructure, it's over 900,000 miles of fiber optic cable connecting the globe. That, if you think about that in maybe a more picture format to wrap your head around, that would span the globe 35 times. 95% of data transfer from point to point occurs across those fiber optic cables. Those fiber optic cables happen to be nominally about the width of your garden hose at your house. So across our garden hose network of fiber optic cables, daily transfers about $10 trillion in economic activity. So this is critical infrastructure for the US economy, for the global economy, for what we do every day. But it's not just related to telecom and communication cables. I'd also mention energy infrastructure. So to think about the scale of the energy infrastructure, we could look at the Gulf of Mexico. We transfer 1.8 million barrels of oil out of the Gulf of Mexico every day onshore to the US. That's about 14% of total US crude oil supply. If we took a look across the Atlantic and looked over to the North Sea and the Baltic Sea, we'd see similar scale of infrastructure there with billions of standard cubic meters of natural gas being extracted from seabed locations and brought to customers in Europe. As massive as this scale of this infrastructure is, it's also fragile. So think about the garden hose again. It's susceptible to natural disasters, it's susceptible to accidents, and it's also susceptible to malicious actors or sabotage. In 2005, off of Taiwan, there was an earthquake, caused some landslides. The ensuing landslides severed 9 undersea cables. That disrupted financial activity and transactions in Asia for about a week. If you fast forward more recently to February of 2024, in the Persian Gulf, there was a large commercial ship that sank, and as it sank, its anchor dragged across a number of cables. That disrupted 90% of the communication capability between Europe and Asia, and 17% of total internet traffic had to be rerouted due to that cable cut. And then more notoriously, you can think of September 2022 and the Nord Stream pipeline and the explosions that occurred near them that were set deliberately and the ensuing damage that caused. So from the Navy's perspective and from a U.S. national security perspective, it's critical that we're being able to understand the health of these undersea networks, be able to monitor them in peacetime, and then in the event of a accident or a natural disaster or worst case sabotage, we're able to quickly assess the damage and understand how to make that repair. So uncrewed undersea vehicles are a key technological component of that capability. They can assist in monitoring the network because they can go deeper than a human manned vessel could go. They can be more persistent. And in some cases, they can even help with the repair of these systems. But the UUV is only as good as the data and information backhaul that we get from it. And so it's critical to the Navy to have a information and data backhaul capability that's modern and that fits the scale of the problem that I just mentioned. We don't need 1 or 2 UUVs operating. We need multiple UUVs, and we need multiple different types of UUVs that are specialized to do different types of things. So with that as kind of a motivating backdrop, I want to step back a couple of years to where we started and take you through a little bit of the journey that we've been on. So the way we used to do business was a UUV would come back to the retrieval point, a sailor would pick it out of the water, attach the vehicle laptop computer to it, download the data from the UUV to the vehicle laptop computer, take that hard drive out of the vehicle laptop computer, put it into the post-mission analysis laptop, And then depending on the vehicle, be presented with one of a myriad of formats, one for each different type of vehicle that we have. And begin the analysis process, which consisted of copying from whatever format that was and pasting it into an Excel spreadsheet. And then after doing a bunch of copy and paste and checking that, you know, the numbers got pasted into the right file and we got all the numbers and we didn't miss any, you know, time steps and we had the timestamps right, et cetera, we might get to some analysis. So in short, it was, took a long time. It's pretty dull. Lieutenant Gregory didn't really enjoy doing this. And it was error prone. And then at the end of all this, we made sure we took good care of our data and put it back into a box or a hard drive or a drawer and kept it for safekeeping. So the team realized that that wasn't going to be sustainable. So we upgraded, and we upgraded to this solution. So I'm being a little bit facetious here. The team that actually started in this work from the beginning was a really smart group of people, really data savvy engineers, and they recognized that, you know, we wanted an enterprise solution, but we just didn't have a way to get there. So we did the best that we could to start off with, which was set up 3 different on-prem data centers for the 3 different locations that we were doing this work at, with the eye towards extending to something that was more global in reach. I think also the team realized that you can achieve this result anywhere. You can achieve this result we had this result on the post-mission analysis laptop. We had it was files that were called like IVR 3 mission report version 2 _ final. You can do it, obviously you can do it on-prem. We got a server closet that, you know, you could make a server closet look like that. And then it's a snap to do it in the cloud too. It's just virtual chaos there. It's data pipelines that nobody understands. It's orphan data stores. So there's nothing unique to the hardware solution that, you know, makes this potential go away. And that's because this is all related to the second law of thermodynamics, right? That applies to data as much as it applies to thermodynamics, right? So entropy is always increasing. You always have to fight the disorder. So in order to get to a data picture that looks like this, it takes concerted effort, and it's not just about the underlying physical infrastructure. The process can feel pretty different depending on the teams that you're working with. Sometimes trying to modernize to a picture that looks like this feels like you're storming the castle. You're met with like locked gates, big tall walls. You get burning oil poured on you as you're trying to upgrade. I've been in meetings where leaders have advocated for the what I would call the Ben Franklin pipeline. That's the data pipeline that highly leverages the U.S. Postal Service, and the pipeline, you know, consists of let's ship those hard drives to the location, let's copy them in that location, put them into a different shelf in that location, and then we might be able to keep track of where it is, or we might not. But the advantage of that, and I've actually heard leaders say this, is that since it's hard for us to keep track of our data, we know that our adversaries can't keep track of it either, so it's more secure. I don't think that's really a great advantage for us. I think we should be taking advantage of the data that we have, and so, you know, it's like I said, it's a constant fight against the second law of thermodynamics. So, fortunately, last summer we had a team of engineers that recognized the benefits that cloud could provide. We had a bunch of sailors that were innovated, motivated, and wanted to work with us. And we had leadership that recognized the benefits of moving in this direction. And so we marched off to transform this data pipeline into a global cloud-based data pipeline, building out upon established processes. So there were some tools that worked very well on the standalone laptop and then worked very well in the on-prem cloud that were not so hard to uplift into an enterprise level cloud environment. Others were a little bit more tricky, but we had a motivated team that was able to work through those issues. We ingested massive backlog of data. We finally got all our data in one place. And the team was very good about sharing across just different lessons learned from the different engineering groups that worked on this. So what does it look like today? So today the UUV still comes out of the water and a sailor grabs it and attaches a cable to the vehicle laptop and copies the data over to the vehicle laptop hard drive, so that's pretty much the same. And then that hard drive gets taken out and it gets put into the post-mission analysis laptop, and then that's where the automation starts. So we use a AWS data sync agent to transmit that data either via Starlink or plain internet into the cloud environment. It lands in the cloud, it goes through some virus scanning. The data that passes through the virus scans then continues on through the rest of the pipeline. And that pipeline's automated. So the operator doesn't even have to select which vehicle is being attached to the front end of this pipeline. That's all automated. So we can't fat finger in and make a mistake and get the wrong kind of data translations. All that stuff's been worked out. Goes there, automated scripts kick off, and we get the analysis done very quickly compared to how it used to be done. And we even leverage some Gen AI tools in generating reports. So now Lieutenant Gregory and the crew that's responsible for understanding how these vehicles work spends their time trying to draw out, how can we change how we operate to be more effective? Which vehicles are operating within the bands that other vehicles are operating in. We found vehicles that, through doing this analysis, we've discovered, this one's INS sensor isn't so great. This one's GPS system isn't working properly, et cetera. The data transfer takes different amounts of time depending on the mission that the vehicle's gone on and the sensors that it has. Typically, for the missions we do, it's about 10 gigabytes per hour of data, and then we transmit that in the cloud. The best time we've gotten is 7 minutes and 46 seconds, if you're tracking that. And then, typically it's more like an hour or just under an hour to transfer this data. We've done it from all different parts of the world, every AOR that we operate in, Indo-PACOM, EUCOM, NORTHCOM. We've done it from multiple different countries, UUVs, and we've done it across multiple different industry partners, US UUVs. So IVER 3, 4, REMUS 100, 600, Gavia, and Anduril dive vehicles all have been used in this pipeline. Okay, so what are the benefits that we've gained from this? Well, one of them obviously is speed of analysis. So what used to take about 1 hour of analysis time for 1 hour of vehicle ops has now been shrunk down to about tens of minutes, and it doesn't matter how long the operation has gone on for. We recently did an op where a vehicle was out at sea for over 30 days, and the analysis, which would have taken, if we'd done it the old way, over 3 months or almost a quarter of human time effort, was done within a few hours. So that's a massive speed up in time savings. It's allowed for better collaboration across our teams. We have teams on the East Coast, we have teams on the West Coast, we have teams on other continents. So someone can pull a vehicle out of the water on the East Coast, start the data download process, and then leave for the end of their workday to go home, and then the people on the West Coast are coming in after their lunch, and they can pick up where they left off and complete the analysis, and so we speed the delivery of the product that we're trying to produce. It's led to best of breed in tools and software. So we host multiple different tools in this environment. Some of those tools are, the Venn diagram overlaps. We have multiple tools that do synthetic aperture sonar analysis or side scan sonar analysis. And so operators can choose, like, hey, this tool really works for me for this job, and then we can feed that back to the developers and kind of start coalescing towards what does the best tool look like for all these different jobs. And then finally, and most importantly, I think it's really led to improvement in the mission. So by looking at the historical data, we've been able to reduce the frequency at which we get fixes for the vehicle. So what does that mean? That means the vehicle can stay deep longer. So it can stay there and do its survey of the bottom and not have to come up and get a GPS fix and still remain within the tolerance for error, that navigation error accuracy that we have and need in order to produce the product. So the UV staying deep has sped up survey times by 2 to 3x. And importantly, the UUV is also more secure when it's deep. So it's not susceptible to being detected by a potential adversary or someone who wants to pick up a shiny object and bring it home. So it's more secure. So the project has really been a great collaboration across multiple different organizations, and it's been a project that's been focused on doing stuff. We didn't write like a lot of white papers and say like we could do this. We rolled up our sleeves, and the teams really got dirty in there with the data and developed a product, and then have iterated and continue to iterate on this product to bring it, more capability and closer to perfection. And it really is a wide and diverse team. It includes multiple different program offices in the Navy. It includes multiple different commands working across multiple different type commanders. So people who report to different 3-star admirals are all working together. It includes federally funded research organizations. It includes It includes other warfare centers and university-affiliated labs. And of course, private industry is involved and a key enabler to all this too. So obviously, AWS is a big partner in this, but other companies are involved too, like ECS is one, Spear AI, among others. So truly been a collaborative effort and continues to be that. So with that, I think I will hand it back to Jeff.
Okay, thanks, Jamie. Fascinating story. Thank you for your leadership, and thank you for the partnership. Just a couple more slides, and then we'll get into Q&A. So many of you are familiar with the flywheel concept. From an engineering perspective, it stores rotational kinetic energy, releasing it to smooth out power delivery from devices like power strokes from an engine. Its heavy mass resists changes in speed, converting energy into spin during high power periods and providing that energy when power is low, ensuring continuous operation and stability. And just on a personal note, growing up watching my grandmother use her foot-pedaled powered sewing machine to rotate the flywheel is another example and a mental model you can use to understand this concept. At AWS, we use the flywheel concept to envision a virtuous process and driving innovation that will lead to customer results and subsequently improve and enable innovation to other areas. This is true with data as well. Data to inform and reinforce decisions, or to validate system performance is in fact as expected. Data to reduce the learning rate between training cycles. And sometimes it's the data that we're not paying attention to that provides us the insights beyond what we're looking for. Jamie just gave us a great story on the navigation system. That's an example of data that we weren't really looking at, but once we got the data pipeline set up, the ability to do the analytics, we're able to discover something that was operationally relevant and important and provided value to the customer. With each generation of frontier model, we see the ability to gain insights that we simply can't do right now because it's too time-consuming, complex, or costly. So being data ready for that next generation AI model is important as well. And so similar to the life cycle of autonomy, at AWS we have this notion of mission autonomy data flywheel, where this data flywheel is an approach that each phase contributes to that virtuous cycle, reinforcing the others. Data from operational deployments improves design processes. Enhanced designs lead to better deployment operations, improved deployments, generate more valuable operational data. And post-mission analysis drives continuous evolution across that entire life cycle. Imagine applying a similar type concept to your data and the importance data plays in your workflow. This QR code will take you to a blog which provides thought-provoking insights into this data mission autonomy data flywheel. It also provides reference architecture on how we've been able to help customers architect the AWS services to enable their capability development. Thank you for your time, and we will be available in the lounge for additional questions. Thank you.